A very good evening to you all. I warmly welcome all of you on behalf of the Mathematics Society of University of Moratuwa to the first session of MTalks for the year 2022. And we are really honored to have you all here with us, as this would be a milestone which will set the path for many more interesting sessions to come this term. And the topic for today's discussion would be on Zorn's lemma. I'm sure all of you would enthusiastically participate and have a fruitful session. Before proceeding with the agenda today, this is a kind request to mute your microphones and switch off your cameras throughout the discussion. And you can raise your questions through the chat box and they will be addressed during the Q&A session at the latter part of the program. So without any further ado, let me introduce today's honorable guest speaker for the session. I have the honor in welcoming our guest speaker for today's evening, Dr. Udaya Jayathilaka. Let me give a brief introduction about Dr. Udaya. Dr. Udaya was an alumnus of University of Moratuwa, where he received his Bachelor of Science in Electronics and Telecommunication Engineering. After that, he completed his Master of Science in Mathematics at the University of Moratuwa. Due to his interests in mathematics, he joined Texas Tech University, and there he completed his PhD related to mathematics. And Dr. Udaya Jayathilaka currently serves as a senior lecturer at the Department of Mathematics in the University of Moratuwa. Sir, it is really an honor to have you here with us for today's discussion. While wishing you all participants an informative and an interesting session, let me hand over to Dr. Udaya. Sir, over to you.
Okay. Good afternoon to all of you. Will you allow me to share? Or can I share myself? Okay, right. So you see the board, right?
Yes, sir.
Okay, right. So thank you for giving me the opportunity to talk about this, which is Zorn's lemma. And so this is a theorem in theory, and so let's talk about it. So this why I thought about doing this is because this came across when I was teaching linear algebra to my semester 4 students, and we had some time to discuss about it, but not enough time. So I thought of doing a talk like this. And let's see how it goes. And I must admit that I'm not an expert on this. So this is a topic in set theory and logic. So, well, let's see. And hope you are able to concentrate, all of us able to concentrate in these difficult situations. And so let's talk about it. So let me start with, semester 1 students are here. So I will make it accessible to everyone participating. And so let's talk about it. And so let's define what a binary relation is. Or from A to B. I think we have done these things. So it's a subset of A cross B. So what is A cross B? Is Cartesian pairs AB, where A belongs to A and B belongs to B. Right? Okay. So what does it look like? So we have so if so this is how it looks like, a subset. We can write this as A related to B also. Okay, so it's basically two elements related. So maybe this is easy to write. So this is A, this is B. So there are some elements connected to some elements on the other side. Of course, there can be multiple connections. Some elements can be left out, right? So, so this is the picture you get. So again, a definition. What is an equivalence relation? So as we understand, so equivalence relation is a relation. Now this time, is a relation. Is a relation are going from a set to itself. So, okay, so the two sets are the same with three conditions. Okay, so number one, for all A in the relation, A in the set A is related to A. And number four, so for all AB in the relation, I'm sorry. So this is the relation. A, right? In A, if A related to B, right, then only if A related to B. So we are ignoring the ones that are not connected, right? So we are ignoring the ones that are not connected. So AB, then B related to A. Right? Number three, also for all A, B, C in A, if A related to B and B related to C, then A related to C. Okay, right? I think these names are even given names. So this is called reflexive, and so this is called symmetric, and this is called transitive. Okay, right. So let's take an example. So we'll define this relation on C to C such that A related to B if and only if A minus B is divisible by 2. Okay, right? So number one, if you take number one, so A minus A is 0, right? So it's divisible by actually some people, there's a way to write it. So like say 2 divides A minus B, right? Divisible by 2. In other words, 2 divides 0. Number 2, suppose A so if 2 divides, so this is because A minus B divides 2, right? So this is because, so this will imply that B minus A also divisible by 2. So this will imply that B is also, related to A. Number 3, so if A is related to B and B is related to C, right? So what does this mean? So that means 2 divides A minus B and 2 divides B minus C, right? So what does this mean? So that A minus B is something like say 2K, and B minus C is something like say 2L or something, right? So if I add the two, I get A minus C equals 2 times K plus L. So which means 2 divides A minus C, which means A is related to C. Right. So this is the situation. Now let's see which elements are related to which. Right. So if you take 0, so what are the elements that are related to 0? Right. So if you take 0, what are the elements related to 0? So that is where the difference between those and 0 are divisible by 2, right? So actually there is a notation for this 0. What does this mean? So this is called the equivalence class of 0. So that means those A such that uh, 0 related to A. So what are these So I mean, I might say equals class of 0. So what is this one? So of course 0 is there, right? So plus or minus 2. So the difference between that and 2 is, right, it's 0 plus or minus 4 plus or minus 6. So all the even numbers are there, right? So I don't have to tell you this is also equal to equivalent class of 2, right? So on the other hand, if I take 1 equivalent class of 1, so those are A's which are related to 1. So that is 1 itself. So plus or minus 1, plus or minus 3. No 2, right? Because 2 and 1 amounts to the difference is 2 and 1 is odd and even is odd, right? So it doesn't divide by 2. So plus or minus 5 and so on. So what is happening exactly is, so if you take the whole of C, did I take C? Yeah. So this will so-called partition Z into 2, right? One is into Z and one is into 1. So that is an observation, right? So one more thing is that we have, what we are doing is we are kind of defining equality. That is why actually even this symbol is used, right? So what we are saying is, although 0 is not equal to 2 as classes, yes, they are, right? Okay. So yeah, if you like, so what the point I want to communicate is that this equivalence relation, right, define equality, right? Define what equal things are. Right? So that is one observation. Right, now that is equality. So check yourself that even equal is an equivalence relation, right? Say in R, right? For real numbers, right? So 1, 0 equal, so for example. So equal, so which is going from say R to R, saying that the relation is equal. It's very difficult right now, right? Okay, so A equals to A. So so if A equals B, imply and implied by, so B equals A. And number 3, so A equals B, and say B equals C, then A equals C, and so on, right? So, well, we have problems because we have defined certain equalities before, but at least that is observation. So new form of equalities can come through this. Now, so in the same context, partial order. A partial order is again a relation. It's a relation. Partial order is a relation. What it does, taking elements from A to A, like like in the previous case, such that number one, so suppose A, B, C, A. So A less than equal. So don't be confused by this. Just think this as any other relation. Or we are using this symbol because it looks like what we want. So A less than equal to A, right? Number two. So if A less than B and B so now I think yeah, okay. So this is different this time, right? So that's the difference. So this is same as previous. Look at that. Which is reflexive. Let me write the last one also. So A less than B and B less than or equal C. That's I say yes, related, I should be saying. And A related to C. So the difference in the second one, so this is same as transitive. So this one, so if both are happening, earlier both are happening, right? So the only way, so this will imply that A equals B, right? So this is called anti-symmetry. Anti-symmetry. Okay, right? So look at this. We are actually using the same symbol as inequality for this relation, which makes sense. So just think about any real number with these properties. So less than equal satisfy this, right? So so a partial order kind of define inequalities. Define inequalities. So the same way that the equivalence relations defined equality, the partial orders defined inequalities. So that's the point I want to make. So a set A on which a partial order defined is called a partially ordered set or a partially ordered set or set. Okay, right? We are never saying that every element is related to each other. Okay, right? So if that is the case, we say that we have a total order. So a relation less than equal going from A to A is a total order if number one is a partial order and number two for all AB in A we have A less than equal B or B less than equal A. Okay, right? So everything is related. Okay? In which way we don't know. But at least one of them should happen. So a set on which a total order defined is called a chain. Right? Why this is called a chain will be very clear when we do some examples, right? So shall we do an example? So let X be a set. The power set Px of the set of all let A power set A equals Px, as a whole subset. Then the set inclusion is a partial order on A, right? So let's see why. So let's take an example further. So let's take X equals 1, 2, 3, right? So our power set is what? Set of subsets. So null set, that's also subset. 1, 2, 3, 1, 2, 1, 3, and 2, 3, and finally 1, 2, 3. So what can we do? So what we can do is we can see which are related by the inclusion relation, right? So what can I do? So we can start with the null set, right? So null set is subset of 1, right? I can put 1 here, 2 here, 3 here. So I'm actually using trying to bring some picture into this, right? So this is true, and then 1, 2, 1, 3, and 2, 3. So this is inside that, right? Also, this one inside that. Okay, so 2 is inside this. So 3 is inside that. Maybe I shouldn't have done this. How can I do something like that? So 3 is here. So 2 is in this. 1 is in both of these. Anyway, so, and then 1, 2, 3, the larger side. So this is, so I think I have to have the larger side here. Okay, something like that. I think my directions are all wrong. So here and then, right, and this one. That is why you do not put any symbol there. I can simply write an arrow, right? I can write an arrow for this. 1, 2, 1, 3, and 2, 3, and simply 1, 2, 3, and the null set. So writing an arrow and writing them, in the increasing direction, I know that it is kind of a greater, right? Greater now in the sense of inclusion, right? In the sense of inclusion. So 2 is related here, 1 is there, 1 is there, and then 3 here and here. Right, so that is it. Right, so this is actually called a Hesse diagram, I guess. So why partial order? Why partial order? Because if you take these two, they are not related, right? So neither 1 is a subset of 2, no 2 is a subset of 1. Okay, right. So this is a partial order for sure, right? So this is a partial order. So do you have chains inside this? What are chains? Chains are, totally ordered subsets. In addition to being able to have some relation, that requires everything be related. Okay, so chains, and as the name implies, so those are the unbroken lines here, right? Okay, so if you take this one, 1, 1, 2, 1, 2, 3 is a chain. So what is a chain? So everything must be, there must be a relation defined on this. Not only that, everything is related to each other. Okay, so this is one example, but let me take a very different example. So in R2, in R2, so define AB less than CG. So I think you have never seen this before, right? If and only if So we are going to compare and see whether we can compare elements of R2, right? So A less than equal B less than equal C rather. C and D less than equal D. So what do things look like here? Which sets are chains, which sets are posets, right? So is R2 a poset itself? So let's draw a picture of R square. So this is XY. So if you take A and B here, is point A, B. So I need the second say the x coordinate be larger than me or equal to that. So I'm basically looking at this, right? And at the same time, I want the second y coordinate to be larger than b, right? So I'm looking at something like this, right? So which are related? Which elements are related by this relation? So if you take AB, anything here is related to AB. In fact, larger than AB, right? So this is the region of interest. And if you take any element here, so you cannot compare the two. So you cannot compare the two. So clearly R2 is not a chain. Right? So by chain I mean not a totally ordered set. Okay, what do chains look like? So, I mean, you should be able to say continuously compare to each other, right? So if you take an element here, I can go in this direction, right? So I can go here, I can keep on going, right? That's a possibility, right? Or if I can start from here, I can even go straight like here, and then go here. You know, it must be in this cone, right? If you like. So if things, the next one falls there, I can do. Okay, so I can go like that also. Right, even here, right? That's fine. So those are what chains look like. Okay. Right. Then, so let's define, let A is a partially ordered set, opposite. So that means we have a relation. So U element of A is an upper bound of A if for all A in A, we have A less than equal to U. Okay. So and well, I have to be a little careful. So let me say let's see the chain in opposite A, right? So we are talking about chains. Okay, right? So U element of A is an upper bound of C if for all A in the chain, right? A less than equal U, right? So that is what. So what do they look like? So we talk about the chain inside the set, and so we are talking about upper bounds. So let's take a look at this. So in this situation, so this is an upper bound for that chain, right? Something in A, which is larger than any element given a chain, right? So if you take this chain, right? So this is an upper bound. Of course, if you take a subset, so if you take a subset like this, so this is an upper bound. Okay, right? So that is, something larger. So everything is, if you take a chain is inside the set A, right? Anything larger from the set is an upper bound. Again, the definition. So M is a maximal element of A. Now we will define this globally, right? For all in A, if M less than equal A, then M equals A. So let me explain. So what we are saying is, remember, not every element may be comparable to M. But if they are comparable, nothing larger than that. Okay? So nothing will be larger than that if they are comparable. So can we have some logical equal answers to this. What I can do is, this is same as, I think you know your logic, right? So I can put not all A in A, M less than equal A implies M equals A. I can do this one. So this is same as there exists A in A. So what is this? So this is like, A implies 1. This is like A implies B, which is same as not A or B. So I have to put not of that, not A or B, so which is A and not B. Okay, so that is so M less than equal A and M not equal A. So remember, this is not usual equality, but we can agree to write M less than A for this, right? So we can have. So I don't have to tell you. So M less than A has similar meanings as less than, strict less than for numbers. Okay, so one can say that this is kind of what do you call this? Strict. We call them strict order. We can call this a strict order. Okay, right? But you get the idea, right? So there doesn't exist an element which is larger than M. Such M is a maximal element, right? So that's the idea I wanted to communicate. Right. So what are maximal elements in this situation? So this is an upper bound, this is an upper bound. So what are maximal elements? So those are elements where you don't have a large element, right? So clearly in this situation, we have only one maximal element here, right? So maximal element is the set itself, right? So 1, 2, 3. Itself. Okay. So what about this situation? Do you have maximal elements here? No, you can keep on going, right? Right. So no maximal elements here. Okay. So, but what you can do is, if you want to have maximal elements, I must change my set. How do I change my set? So if I take, for example, something like this, right? Suppose I call this the set I want. So suppose this is the set A. Then what are maximal elements? So what are maximal elements? So you change, go like this and hit that, right? So maybe change, go like this, hit that. So this will be the, so there may be more than one maximal element. Maximal elements now live on the boundary. So this being the set. Okay. Right. So are we in a position to talk about it? Yeah, I think we are there, right? One more notice. So I think we will have to talk about this a little bit more. So if you take the set of natural numbers, 0, 1, 2, 3. So this is a chain itself, right? So this is a chain itself. Everything is related, right? No. So with usual less than equal inequality, no maximal element. But, so I mean, if you look at this, so this is a chain by itself. So this is keep on going, right? 0, 1, 2, 3. This is keep on going now into this. But if I do, what doing this? Suppose I join n with something like ABC and enforce A, C is larger than A, B, or C. So what is the picture we have? So we have this picture where this is 0, this is 1, this is 2, this is 3, this is keep on going, right? So this chain does not have a maximal element, but this chain does, right? So ABC. So this is the maximal element, right? Why? Only if they are related that we have to worry about it, right? Only if they are related that we have to talk about it. So there is no element in the set which is strictly larger than M, the maximal element, right? So this is a maximal element, right? Also, so to notice that, unrelated and if you have single element somewhere, that is also maximal, right? Because there is nothing above that, not even related, right? So unrelated elements are maximal. Also, they form chains. So let's call this D or something. So I'm just putting D, but don't enforce anything on that, right? Form chains, for example, in this situation, D is a chain. Okay, so that is totally ordered by itself. So, yeah. So even null set is a chain. Why? Because there is no element. Because there are no elements to do a comparison, right? So what is a chain? So if you have the other conditions satisfied, so we have to have if A be element of the null set, then A less than equal B, or B less than equal A. Well, so this is false. So this becomes true. So null set is a chain. So singletons, as they call them. So like this is a chain. And standing along elements, singletons are maximum. So those are things we infer from the definition. Okay, right? Now, the theorem. Zorn's lemma. Let A be a O set, that is partially ordered set, and every chain in A has an upper bound in A. Then A has a maximum element. So this is the well celebrated Zorn's lemma. So what is the intuition behind this? So what we can do is we can try to violate the conditions, right? We can violate the conditions and see whether we do not get what we want. So why every chain? So let me ask a question like this. Any situation where Zorn's lemma fails to detect a maximum. So our attempt is to detect a maximum. That is what our goal is. So the Zorn's lemma says, okay, check every chain and make sure that it has an upper bound, right? Then A, not this particular chain, right? Then A has a maximum. So one way to understand this is to identify a situation where Zorn's lemma actually failing to detect a maximum. Where? Can anyone give me? Do you have an example? Do we have an example where the Zorn's lemma is phased to detect a maximum? Hello, are you there? Is this too technical? You get my question, right? So you know what maximum elements are. Okay, so those are elements where I don't have anything larger. So I'm asking a situation where can you give me a set and a relation, of course, and a way to compare them, where it fails to detect this maximum? Yeah, answer, we already did that, right? Isn't it? So let's check this one. So rather the conditions are not satisfied. So if I do this one as the set, so so in this chain does not have an upper bound, right? So this chain does not have an upper bound. Okay. So, one chain fails, everything fails. So it doesn't matter. I mean, it can't detect this one then, right? Because it's a chain but has a maximal element. But, because one chain fails, everything fails. So, the Zorn's lemma can't identify this maximum. Okay? Not identified by Zorn's. So that is, that's theorems. Theorems are like if then, right? So then if fails, who knows? Anything can happen. So that's a normal thing, right? Then let me ask, then why can't you check some chain someday? Why can't you check? Why you have to check? Any idea? Why do you have to check every chain? Hello, are you there? So why do you have to check every chain? For example, in this situation, let's take this situation. Remember, subset of a chain is a chain, right? So if I take 0, 1, 2, 3, 4, so this is a chain, right? 0, 1, 2 is also a chain. So 3 is an upper bound. Okay. Yeah, then can we be happy about the situation? Absolutely not, right? Because there are some chains like this one, which is not having any upper bound. So you have to check every chain, right? So we have no option. So as an application to this, so let's use this for something. So application. So we will prove that every vector space has a basis, right? So for those new people, like in semester 1, so let me remind very quickly what a vector space is. Okay, vector space. What is a vector space? V over the field F. So I'm not going to tell you what field is. Semester 1 people know what field is. So field is something like R, right? Okay. So what is a vector space? Vectors, vectors are a vector space. So what are we trying to do? As we do in mathematics, all the way. So we generalize the ideas of we generalize the ideas. That's how we go forward in mathematics. So we are trying to realize vector space, vector-like things in non-vector-like spaces, sets. How do we do this? One. So remember, vectors like, say, 1, 0, 0 can be added to other vectors like 2, 3, 4. So there is this vector addition going on, so which we call star, right? For all x, y in V, so we want x star y be in V, right? So if you add the two vectors, you get a vector 3, 3, and 4, right? Number 2. So then you must tell how to add 3 vectors, right? So C equals, so x star y star C. So this is for all x, y, C in V, right? So that is true. Number 3, so there exists a E in V such that E star x, so this is for all x in V, where E star V equals V star E equals V. Now what does that look like? So this E looks like the 0 vector. So if you add 0 vector to any other vector, right, ABC, you end up with ABC. That's what we are saying here. Number 4. So for all x in the vector space, there exists a vector we actually call x bar, where x star x bar equals x bar star x e, right? So what is that? So that means there are, so for each vector a, b, c, you have a negative vector. Then you add, giving you the zero vector, right? Okay, so which we call yx bar. So this is not a surprise. I think people and finally we will so for all x, y, v, so x star y equals y star x. So this doesn't matter the order in which you add the vector. So these are called abelian group. Okay, right? So if those things, so if you have an operation like this, and if you have a set, and if you have these 5 properties, so that itself is called an abelian group. So number 6, F is a field. Okay, so that is number 6. But in a field, can you remember? Field has 2 operations. Field has 2 operations, which I call say plus, right? What is plus doing? Take elements of F, take 2 elements of F and produce an element of F, and take an element of, so there are 2 operations. One is addition and the other one is multiplication. I mean, we can. So F. So it has 2 operations, right? So I don't have to tell you, right? And of course, inside F has 2 abelian groups inside. So what are those? F and plus, right? So replace V by F and star by plus. You get the same thing, right? You get the same thing. Okay, so like replace V by F and star by plus. You get the same rules, right? Also, F minus the zero vector is what is associated with plus, right? So E for 0, I'm saying 0 is E for plus, and 1 is E like this E right there, okay, for the multiplication, right? So this is also an abelian group. 2 abelian groups inside. Right, I think that's enough. And number 7 is how these things go together, right? So this is a field. It has 2 internal operations, and V has 1 internal operation so far. And then for all x in V, so there is a way to multiply vectors with numbers. So we'll call this A naught x or something, which is in V. Now what does it look like? So you can multiply. So if you take the field as R, and if you take my vector space as say R3, so you can multiply vectors by numbers. See, so like 2x 1, 2, 4 is 2, 4, and 8, which is a vector again in R3. So that is what we are saying here. Number 8, now how the distribution works. So for all xy in V and for all A in F. So if you have A times, so this is scalar multiplication, right? So we call this scalar multiplication, whatever I do. Okay, so x star y equals A and x, that is an element of V, then star with A star y. Okay, so number 8, no, rather 9. So we can have two numbers. So remember they are plus, they are combined by plus and scalar multiplied with x. How do we do this? A naught with x and then B naught with x, but be careful. So these are vector elements now. So it's star that should take. So plus becomes star if like. So there are differences, right? There are differences. So what else? What else? All x in V. We can do a two multiplications also, like 3 multiplications. So what about doing A into B? This is in F into X. So this is A into B into X, right? So that's also possible. See, I mean, these things are different, right? Although we are so used to it, right? So, I mean, this is like saying 2 into 3 into vector 6, 8, 10. So what we are saying is this is equal to 2 into 3 into 6, 8, 10. That's what we are saying. But, you know, this is number multiplication. This is vector number multiplication. This is vector number multiplication. And this is again the vector number multiplication. So these are different. Yeah. So number 11, finally. So for all in x, we 1 into x is x. So what is 1? 1 is this fellow right there. So the identity for the multiplication operation, right? So yeah, but you know, we can't keep on doing this. So at least you know the differences. So we will simply write plus 4 star and so on, right? Plus 4 star dot 4 not and what else? 0 vector for E and so on, right? But without confusion. Same symbols used in, for example, same used in R3, for example. Right, okay, so now I think we are there. So let B be a subset of V, right? So what is V? A vector space. So span B, so what is span B? Those are all possible finite sums of so how do we do that? So A1, say V1 plus. So remember we agreed to write them like simply plus without writing star. So A2, V2 and so on. AN, VN, where VI in V and AI in the field, and N is an integer. I'm saying so any positive number, right? So well, I'm starting with 1, so what we are saying is, so this is like what? So there may be more elements. So I'm not saying Vn, there are only n elements in Vi, right? So what I'm doing is I take a finite number of them, finite number of elements of V, and select the same amount of field elements and combine and get the sum. So I do this for all such combinations, right? Why only for finite sums? Why finite? So I'm simply writing finite sums, right? Of AI, V, I, something like that. Okay? So why finite sums? I think if we have infinite sums, we are in trouble. We have to appeal to real analysis and so on. So yeah, we will never be able to do those. Okay. And B is linearly independent. So what is my linearly independent? So if we have any finite sum, A1, V1 plus A2, V2 plus A and Bn equals 0, where AI is in the field and Vi in V. So this should imply that all the coefficients are 0. Right? So this should happen for all n, right? Okay, I don't have to tell you. Right? So when I say n, I have to consider all n. So this is the situation, right? So I mean, maybe I should write. Maybe I have to put this one in front. For all, say AI in the field, So for all vi in the field, if a I A1 V1 plus A2 V2 plus A and Vn equals 0. So implies A1 equals A2 equals N equals 0. So yeah, so they have nothing to do with each other, right? So what we are saying is elements of B, if they are combined to 0, then actually there is no relation between them. So only relation is the 0-0 relation, if you like, right? So one cannot be formed by the other. So if you try to form a relation between them, a combination between them, then it tells you that there is no relation, no combination, no relation between the two, right? So if B is linearly independent, so Li for short, and span B equals V, then we say that say that B is a basis for V. Now let's take some examples real quick. So if you take R3, give me a basis. R3, so with the field being R, okay, what is the basis? So this is a basis, right? So look at this, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, why? So if you multiply, so what we have to do, we have to run through all the finite combinations of this one. But I don't have to do that. Why? Because when I run through all the combinations like A 1, 0, 0 plus B 0, 1, 0 plus C 0, 0, 1, I automatically get the situation where these things are 0, right? So I don't have to individually check for this one in the span, right? Okay, so yeah, I don't have to do that. So just take so what I'm saying is when the set is finite, go for the whole combination, full combination. Right, so what is this one? So this is the span of B, yeah, ABC in R. So obviously I get ABC yeah, ABC in R. So I get R3. Right, so linearly independent. Yeah, so if A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1 equals, which is ABC, equals 0, 0, 0. Remember, this is my 0 vector. So implies A equals B equals 0. So B is a basis for R3. So I'm letting you do this. So also B equals, say 1, 1, 1, 1, 0, 0, 1, 2, right? And 1, 1, 1 is a hook, is a basis of R3. right? So it turns out to be that you just need 3 elements, linearly independent ones. So one way to check the linear independence is you check the determinant, right? So what is the determinant? So this is 1 times 1 minus 2 minus 1 times minus 2. Right? Which is 1, not 0. So linearly independent. So you check y, right? Anyway. Right. So now let's take another example. So Rx. So I'm using this to say polynomials in X with coefficients in R. Okay, over the field. So what is the field? Let's take R. So you check all the things, right? So if you take 2 polynomials and you get a polynomial, which is again a polynomial, right? So if you multiply by a polynomial by a number, that's a polynomial, real coefficients, right? So and so on. So I'm not going to check things. But now what is the basis? I'm not specifying the degree, right? I'm not specifying the degree. So what is the basis? Come on. So something like this is a basis, right? So 1x squared, x3. How many elements? We can't stop, right? We have to have all the powers. But remember, given a polynomial in Rx, we need, you check this one, right? We need only a finite number of xk's to form it. So what I mean, now any polynomial is a finite, it has, it must have only finite powers. Say 5 times x to the power 100, right? Plus 4 times x plus 3, right? Say pi. So what is this one? So this is an element of this somewhere. X is already there. So pi is fine to 1, right? So this is in the span of B. But remember, we need infinitely many elements, right? So here, countable number of them. Here, number of elements. I say countable number. Here only a finite number. So then, another example. Say V, CAB. So this is continuous functions on AB. I think you know what continuous functions are. I'm not going to tell what that is, right? Over the field R. So what is the basis? Well, do you think it will be countable, finite, or uncountable? Right? So it happens to be that a basis will have uncountable. What do you mean by uncountable? I think you know from your semester one. So like R, right? Number of uncountable number of elements. So I say no, basis will be uncountable. Okay. Right. So you can't say 1, 2, 3, 4. So what is that? What is an example? I don't know. So anyway, so we can show, look at this, how complicated task can be. It can be finite, it can be countable, it can be uncountable. Now, just the interesting thing is, think about using a finite number of elements. In a basis to write any continuous function on it. That's interesting, right? But it can be done, right? So the theorem will be that any vector space has a basis. Right? So if you start with trivial case, if you like. So check, so this is a vector space. So if you have only the 0 elements, that itself is a vector space. So we will define with good reasons. So define null set to be the basis. Okay? So otherwise assume that my basis is assume my vector space V is not the null space. Okay, right? So proof. Now this is where we are going to use the Zorn's lemma. So So let D be the set of linearly independent subsets of V. So remember, this set is linearly dependent, right? So you check is linearly independent. Why? So why is the case? So if A into 0 is 0, so that doesn't imply A is 0, right? Because you can have any element, say 2. 2 into 0 is also 0, but 2 not equal 0. 0 number. So what we are saying is that 0 vector space, or rather 0 vector itself, is not a linearly independent set, right? So here, because we are saying that this is not equal 0, we have some linearly independent subsets. Okay? So since V is not equal this one, D is non-empty. So we can work on that. So this is the set D, right? Let C be a chain in D, right? So what is the operation? So under inclusion, right? Operation is inclusion. So what does Zorn's lemma need? Let's go back and let A be a poset. So partially ordered, so no problem with that. Okay. So we are talking about some subsets. So they are comparable. So every chain has an upper bound in A. Now that's what we want, right? So let's C be a chain, right? So we need an upper bound for that. So what is a chain? So that is a sets of subsets, right? So it's like C1, C2. So actually it's kind of very dangerous to write these things. So one might think that these are countable, not necessarily, right? Okay. So yeah, chain indeed. So the claim the union Ci, Ci element of C is an upper bound of C. Why? Well, so for all Ci in C, so Ci is smaller than included in U. So that is an upper bound for sure. But upper bounds need to be inside the larger set also. Upper bound in D. So the question is, so we want U to be in D to claim a maximal element. So how do we do this? So what I'm going to do, I'm going to take some finite number of elements, x1, x2, xn, in the union, right? And let x1, so a1, x1 plus a2, x2 plus a3, x3 equal to plus an xn equal 0, right? So what is meant by in D, we have to show that this is linearly independent, right? And spans, okay? So U is linearly independent, okay? So let's talk about the spanning later, right? So U is linearly independent. That's what we want to show. So let this be 0. But, so what is U? U is union of certain things. So if certain element belongs to the union, so they exist, say Ck, an element of C, such that Xk is an element of Ck, right? So that's understood. So if you take any element of the union, so that element must fall in one of the elements in the one of the sets in the union, right? Maybe few fall in the one set, that doesn't matter, right? So it's okay. Now what? Now, so if I take all the, so some of them may be same, that doesn't matter. So if I take the union, so C1, C2, Cn, of these guys, that is again an element of the chain, right? So do you get that? So what do you mean by a chain here? What do you mean by a chain? Chain means in this situation, so if I take two elements, Ci, Cj in the chain, so that means either Ci is a subset of Cj or Cj is a subset of Ci. So if you take a finite sum like this, so it becomes one of the elements, right? So Zm is in C, right? Now what do you have? So obviously, this xk's belongs to, so for all k, xk belongs to this new member of the chain. and CM is a member of the chain. Chain is inside the linearly independent subsets, right? So shall I write, I mean, although this is bad, but shall I write something like this? All right, this is a chain. So CM is somewhere there. Okay. So that is linearly independent. So what does it mean? And of course, we have its elements are combined to 0. And we have A1 x1 plus A2 x2 plus AN xn is 0. So what does it mean? That means A1 equals A2 equals N equals 0, right? So that means what? Now, if you look at this, we started by saying that these XSR belongs to U, and now we are saying that if they are combined to 0, I'm getting the coefficient 0. So this means what? U is linearly independent. So that means U is in D. Yeah, so we got it. We have an upper bound now. Right? We have an upper bound which is linearly independent, which is in D. Right? So what does it mean? That means D has a maximal element. B, where? B in D, the linearly independent ones. Now, so we have established that we have a maximally linearly independent B, right? So we have a, I mean, we don't have to use that term. We will prove that later. Anyway, so we have a maximal element in this chain. Not in the chain. It has a maximal element in D, right? I'm not talking about this chain, right? Okay, I'm talking about in D we have that. Okay, then what? So suppose now I don't have to tell you that span of B is inside V. Why? Because B is a subset of V, right? So if you combine any elements of elements of B are elements of V, any addition and in a vector addition and scalar multiplications fall inside V, being a vector space. So span B also falls inside V. Now assume, so what we want to show is that span B equals V. Now assume that span B so is strictly inside V. So if you can look at the picture. So this is B, this is span B. So they are not equal, so I can find the X there, right? So take an X in B minus span of B, right? Now consider another set, say B prime, which is B union this new element, right? And what do I do? So with Vi elements of B, what I do is I form a sum. A2, B2, and Vn plus say B times this fellow, X right there equals 0. So two things can happen. So number one, if B is not 0, what will happen? If B is not 0, so Xc will be equal to minus A1 by B, V1, minus A2 by B, V2, minus and so on, minus N by B, Vn, right? So these are field elements. Remember, these are field elements. Why? Division is multiplying by its inverse and so on. So this is in the span of B, because this is done by finite number of combinations of D. But can X be in the span? No. So this is a contradiction. So that implies that B equals 0. So if B equals 0, so we have A1, V1 plus obviously A and Vn equals 0. So that implies A1 equals A2 all the way An equals 0. Why? Because B is linearly independent. That is how we element of D is linearly independent, right? So what is that? So this will imply A1 equals A2 equals N equals B equals 0. So that means, so I'm combining n plus 1 number of them, if you like, equal to 0. So if X and other things are combined to 0, the coefficients are 0. So that means B union X is linearly independent. So B union X belongs to D. But remember, we said that B is maximal. But I don't have to tell you, B union X is strictly larger than B. So B can't be maximal. So we have a contradiction for the second time. So if B is not maximal, so this assumption is wrong. So span B equals B. Also, I don't have to tell you that we already proved that B is linearly independent. So if any linearly independent, that spans the vector space. So B is a basis for B. So can you give me like 30 minutes to complete this? Or are you tired? Or who are the organizers? Or you do have any questions? Do you have any questions so far? So if I want to, yes? Yeah, I understand. But I was thinking of giving some hints to prove the Zorn's lemma. What shall I do? Let me actually state them, right? Okay, just state what is so equivalence of source lemma. Number one is the well ordering theorem. There are a couple of them. Ordering theorem. So it says that every set can be well ordered. In other words, there exists